So we are approaching our last lecture of the year / unit on the albedo effect. Before we get into that, I asked you guys from yesterday's lecture on feedback loops, connecting that to melting ice and thermal expansion. All obviously in the effort to eventually answer the question, will we lose our Santa Barbara beaches, based on examining the phenomena of global warming effect on sea level rise. I asked you guys to answer the question question number 5 on unit 6, understanding how does collision theory begin helping us understand why we see thermal expansion, and then putting that all together with the previous material to answer this question. Summarize the relationship between the event of thermal expansion with the observable sea level rise, which involves actually a lot of things. That incorporates more than just thermal expansion, sea level rise. That incorporates, if you're going to talk about warming, well, why does it warm? Greenhouse gases, right? So I'm going to give you guys about 3 more minutes before we discuss and share to kind of finalize a summary. This is one of your practices for the test. These summaries are your practice, okay? Because you don't have an official workbook for this unit. So go ahead and do that for about 3 minutes, and then I'm going to actually ask people to share. So can I have one person please share their response, even if it's not finished, even if it's not the most eloquent version of it, using your unit 6 understanding on collision theory, explain what is happening to the particles when heat is applied. Aislinn?
Basically there's more colliding. So heat causes collision within particles, which makes them move faster, and collide more, which makes them spread out more because you need space to do that.
Okay.
So in this case, the sea levels are rising because they have this colliding particles of no.
Okay, so one aspect of the sea levels rising is that. So that's a great, let's isolate. This question was particularly, I think, just heat and thermal expansion. And then you started working in the summary part of connecting it to sea level rise. But absolutely correct. So as you have more heat, or what you see is when exposed to heat, okay, you're gonna see that the particles collide more because when exposed to heat, they absorb that heat energy, using it to increase their kinetic energy, creating more collision, creating more pressure buildup between the particles, right? If you start colliding with more force, okay, you're gonna naturally start wanting to expand. And if you don't have boundaries, you'll just expand until your energy stops you, but not your surroundings. So here's the thing, as particles collide and they have more kinetic energy, it will result in natural expansion with respect to the set boundaries, okay? And as far as the oceans goes, the oceans don't really have a boundary. The only thing that really keeps them in check is the gravitational pull of the moon. But as far as like, is there a wall that stops it between like the water and us? Not really. Not really. Like the shelf doesn't do that much, right? It's not going to stop a tsunami. In fact, it actually helps the tsunami get an arc that takes you out. So shelf isn't that helpful. So now let's take that particular focus on connecting unit 6 thermal expansion and kinetic energy and collision theory with now tying in a bigger picture of, okay, how do we explain thermal expansion's connection with sea level rise? And really what that means is you're going to also have to mention greenhouse gases, because why do you even get heat in the first place to cause thermal expansion? Okay, what's the feedback loop that's happening? Will sea level rise ever stop? Theoretically, if we keep on having heat, no. Theoretically, no. So how did someone kind of tie this together? Mika?
Well, technically, even with
without the CO2 and heat that we're producing, this would still happen, just at a very slower rate, because the earth does heat up.
Oh, sure. Yeah, very minimal. The concern is more the increasing heat. Not that there's heat itself. We need heat to survive. We're not going to live on an ice age, and hence there is no life on the ice age. But there's a lot. Okay. DreamWorks and Pixar, thank you. Anyone kind of have like a little summary, even if it's not perfect, even if it's just part of it? Yeah.
As the water particles in the ocean heat up due to the heat being trapped in by greenhouse gases, they move and bounce around more, creating more space between each particle, expanding the ocean, causing sea level.
Excellent. That's really nice. So I'm going to do a flow chart. It's your job to put into words, but I'm going to take your beautiful, eloquent little spiel and then put it into a flow chart. So basically what we have is, according to Hallie's, explanation, she started with the idea of, where do we even get heat? Well, we have greenhouse gases in the atmosphere that trap IR. What does this do? It raises, the heat in the atmosphere. Okay. What does that mean? That means that the temperature or / heat content increases in our world. Okay, if it increases, what we see is that we melt, ice. Okay. So we melt ice. We actually see two things. It kind of goes two ways. We melt ice, and when we melt ice, we actually add to the volumetric count of water. We add water as it drains. Okay. But we also see, kind of adjacent to that, we see that as heat temperature increases, we see the already present particles in general gain heat energy. So the particles collide more, which means that we're going to see thermal expansion. Oh, gee willikers. I'm writing too low. Thermal expansion. And that together, if you connect these two, both contribute to sea level rise. And if you want to get really specific, you could talk about the feedback loop. Where you could see a feedback loop with the melting ice. And you could talk about even a feedback loop with what I'm going to introduce next, the albedo effect. So that's kind of like if you really wanted to get the bonus in of talking about, well, how does this build on one another then? Well, if my sea levels are rising, I have less ice. When I talk to you about albedo effect, you could also say, oh, I have less reflecting light, which means my ocean with more water in it is now absorbing more heat, warming up our Earth's surface even more, making the little ice remaining melt even more, adding more water, reducing reflection, increasing our ability to absorb heat, creating more heat. If we're interpreting the data correct. And again, even if this is all true, right? This is all true. Maybe we don't care. We haven't mentioned anything about time. Like, we know it's building, but what if it's accelerating at a rate that's we'll be dead anyway? So I was like, well, I don't care. Our future children can die. We're not going to be around for it. Hopefully. Right? Like, that's totally a fair take. For survival of the fittest, it's a natural ebb and flow. We're gonna relocate to Mars anyway. Like, lots of arguments that can be made. It really could not matter. We could even say that this is going to be outcompeted in like a pendulum swing back of the environment, maybe hitting a point where it starts reversing things in response to, all of this stuff. Who knows? You can make an argument. We haven't addressed any of those arguments yet. We're just looking at, what does this data tell us? What do the principles teach us and how to interpret that data? And then do we think that when we approach that data with the principles and our understanding of it, do we think that this is a valid interpretation? Or maybe it's not. Maybe it's just not enough information yet. We haven't considered all sides. Totally fine. Anyone can argue anything pretty much. Okay. So, good. Any questions with that? All right. So let's kind of dip into our toes into this whole idea of feedback loop with the melting ice that Bill Nye mentioned in the video that we watched yesterday, which was this idea of reflective light, that the ice not only, okay, holds water, especially land ice, land ice, okay, keeps water out of the sea, but it also is really actually an important cooling effect, not because ice cold, but because ice reflects light. And we call this the albedo effect. It's a much bigger topic, but the big idea here is that albedo, this concept of albedo is really talking about the idea that a percentage of visible light is reflected by materials or surfaces. Kind of like how you know that white light, when you shine a light on something white, it comes back at you worse, right? When you shine a light on something dark, you don't exactly fear that it's going to reflect back on you unless you have like some gloss over it. But an actual dark color doesn't reflect light very well. It's why you don't want to wear black in the summer because you tend to get hotter. My head of hair, I have pretty dark natural hair when I've, like not dyed. Okay. It gets super, super hot. I've burnt my hand on my head from being in the sun because my hair has absorbed so much heat. Okay. I don't find that many blonde people tell me that when they touch their head of hair, in a hot summer day that they feel it's super hot. It's usually just their scalp at that point burning. Okay. So it's kind of something that's small that we experience every single day that is incredibly important for understanding why people are freaking out about the melting ice. Not only because the melting ice on land is adding to the sea level content, but it's also removing an actual cooling effect. It's removing a negative feedback loop that we want. Okay, so when you look at albedo, what you want to know is that the greater the albedo, okay, the greater the reflection, which means the more cooling. So we want actually higher albedo, at least for the context of where we think the climate's going. If we thought the climate was cooling, we would not want albedo. We would want to minimize that, right? We'd want to keep the Earth's surface warmer. So an albedo of 0, and it's on a scale of 0 to 1, an albedo of 0 means that 0% of incoming light is reflected and 100% is absorbed. Okay, an albedo of 0.3 means that 30% is reflected and 70% is absorbed. Are you seeing the trend? If I have a 0.7 albedo, how much is reflected? Yes. How much is absorbed? Oh my God. If I have a 1 albedo, how much is reflected? Excellent. So what we have here is when we look at white surfaces, they actually have an albedo. True white surfaces have an albedo of 1 or 100% reflection. And then while black surfaces have an albedo of 0, 100% absorbance. Okay. For example, Venus is very bright in the night sky because it is surrounded by clouds. Clouds are highly reflective for the most part. Okay. That reflect a large fraction of the incoming light. It's why cloud coverage cools the area, not because the vapor is all that dense. It's not like the sunlight can't pierce through the clouds, which is, by the way, why you should still wear sunscreen even on cloudy days, because the UV lights aren't necessarily being stopped by the clouds. It's not an actual metal blockade, right? But what it does do is that the light rays that do hit the particles of the cloud, because it's a white surface, it's a white property with high albedo, it sends it back up. So it creates a cooling effect. That's why you're cooled by clouds. Not because clouds are actually protecting you from anything. Really. They're not a big metal slate in the sky shielding you. You will still die if hail comes. Like it's not protecting you. If a meteorite comes, the cloud is not going to save you. Okay? But this is why. So the Earth, by contrast, has fewer clouds and large expanses of dark ocean. Ocean is a huge absorbent. Ocean is low albedo. Thank you. Oh my God. Low albedo. Okay. So what we see here is that because of the fewer clouds and large expanse of dark oceans, which averages to an albedo of only 30% versus Venus, so that has an albedo of 78%. Okay, forests also trap a lot of the incoming light. So forests are also a low albedo material on Earth, geographical feature on Earth. Okay, they reflect very little sunlight, which gives them an albedo of only about 10%. So right now we have, geographically speaking, on Earth, 40% albedo, which is like better than nothing, right? Better than nothing. But if a lot of our albedo sources, which include land ice, is melting, that 40% is not staying constant. Now we are deforesting, which could be argued as helpful for greenhouse gas trapping heat, because if forests are a big sinkhole for heat, then we could be saying, oh, if we deforest, we don't have to worry about as much heat being absorbed. But forests are also a huge sinkhole for carbon dioxide gases. So you're really wiping yourself out on both ends of the spectrum by deforesting, which no one in construction talks about. All these big project plans, no one's thinking about how we're literally slicing off the good parts on both ends that help us by deforesting, let alone just the pretty nature. Biologically speaking, the habitats, right? Which is where a lot of advertisements kind of rip at your heartstrings, right? They play that "On the Arms of an Angel" song, and then there's like a little bird like with a little wing that's broken, right? And you're just like, oh no, my little crappy salary, I will give them all my money. And it's like, okay, well, yes, that's good too. But they never talk about the actual environmental impact that actually lasts years and years. Theoretically, communities of species can grow back, right? You breed them, your little pool, you go, okay? But yes.
It's also possible too, because there are still people that don't, it's a harder, if it's not something that people can see, people either won't believe it or just don't care.
It's true. It's true. No one looks at the forest and is like, I see the heat absorbing. Wow, that is a high heat absorption day. Look at that Amazon. Look at that ton of heat. No one says that. No one also says, look at the forest. 70 cubic tons of carbon dioxide. There you go. Well done. Well done. Right? No one says that. So that's totally true. We are such creatures of visual nature, okay, that it's very hard to believe what we don't see. Right? So this is kind of just like a little bit of background on why this topic of albedo is just so incredibly important, and why it's also a very significant factor in understanding the feedback loop systems that we see. Okay, so why is the albedo of Venus higher than Earth? And clouds have, it has more clouds, and clouds have higher albedo, which means greater reflection, which means, okay, more cooling effect. So go ahead and quickly fill out this little chart of labeling high albedo versus low albedo. All right, so surface, blacktop, low or high? Oceans, clouds, fresh snow, glaciers, forests, deserts, high albedo. Deserts just reflect.
But it's hot.
Okay, just because a forest is cool or hot doesn't mean that tells you how much heat they're absorbing in terms of UV and IR rays. But deserts are high albedo. They reflect. Remember how we talked about how deserts and soil have low heat capacity? They have a low ability to absorb heat. High albedo, more reflective. Well, that depends on their exposure to the sun and other things, but yes, there's many wavelengths of energy. So, okay. So complete the feedback loop below using the word bank. So I want you guys, what we have here is global temperature increase, this phenomena. Label the input, label the change or the mechanism, and what's the overall output or result. And then identify whether it's positive or negative. Go ahead and do that. So what do we put for our input? We have the phenomena, global temperature increases. What do we put for our input regarding albedo effect? Reforestation. Okay. What's the kind of mechanism or change that occurs? More tree cover. So then what's the output? More light absorption. Okay, less light reflection. Global temperatures increase. Is this a positive or negative feedback loop? It's positive because what we see is, well, I guess I could see how you would want to say negative because you say less light reflection, right? But what the idea is that our response increases the input. Our output increases the input. Okay, so it's positive. Our output enhances the input of global temperature. We come right back to it and we're like, oh no, right? When you add trees, you have lower albedo. So, okay. Yeah, you're right. Trees are great for carbon dioxide absorption, not necessarily light absorption, different. Okay, so here's what you guys are gonna do now. All right, what we have here is I'm gonna get out a couple articles for those of you that want physical. You have 2 articles. This is the one time I'm gonna give you where you kind of can look at a little bit of a firm versus a challenge. This is also hyperlinked in your student notes. It's also hyperlinked into my website, and you're gonna read these 2 articles, okay? And you're gonna look at some data. And you're going to use those articles to answer your final question, which is also going to be extra credit into your assessment category of your test. It can boost your grade. This is about a 2% right here. This is a 2% value of boosting, okay? You're going to read these articles, and together with your notes, you're going to write up an answer to the question, will we lose our Santa Barbara beaches? It is your practice for the test. It is also practice for looking at data that you will look on the test, different set of data, but it's going to be your practice. So that's what the rest of the class is about. This is your study for the test. So I'll get out prints of the articles right now. I have limited. Otherwise, everybody read the affirm versus challenge article via digitally and go ahead and spend the time writing this up. Good luck, you guys, and congrats. That's the end of your last lesson.